Hey folks, so sorry that the audio cut out on the lecture. We're gonna try to make sure that doesn't happen again, but for now, yeah, I'm just gonna try to walk through the lecture, especially to parts we didn't get to actually in lecture, so this will be more full than the lecture, but also not polished and not interactive. So yeah, let's just kind of get through what stable matching is remotely. So let's see, right here we have some preferences. So if you haven't taken a look at the stable matching problem, we have 4 people, 1, 2, 3, 4, and they have preferences for 4 other people, A, B, C, D. So 1 prefers A more than it prefers B, more than it prefers C, more than it prefers D, and so on. So C prefers 1 the most, 2 the second. Actually, this one just goes right in order. 1 preferred to 2, preferred to 3, preferred to 4. So each group of people have their own set of preferences. Whoopsies. Have their own set of preferences for each of them. And kind of the goal is how to match them, right? 1 would love to be matched with A, right? 1 would love to be matched with A so that 1 and A are together. But A actually likes 1 the least. So whatever matching we end up with, we're going to have to take everyone's preferences into account and try to come up with quote unquote a good matching. And we'll need to talk about what good means. But for now, we're just going to look at the algorithm that does this. So we're making a little bit of a transition in the semester. That is, up to this point, we've been kind of learning about proofs from the ground up. How to prove adding 2 even numbers is an even number and so on, and being really rigorous about that. And we've gotten all these proof techniques. And now we're going to try to start moving more towards computer science and talking about algorithms and seeing if we can use all these tools that we built up to prove things about algorithms themselves. So we're not going to spend too much time on recreating the algorithm from scratch ourselves. We're just going to go ahead and look at an algorithm and prove things about it. So let's just take a look at what this algorithm does. It's called the proposer-reject algorithm. Sometimes it's called the Gale-Shapley algorithm, the stable matching algorithm. There's a whole bunch of different names for it. But what it does is it takes a set of preferences like this, and it matches people based on those preferences. So let's just take a look and see what it says. This is the whole algorithm. It's pseudocode, but this is the whole algorithm. It says each proposer proposes to its top choice. Each rejector rejects all but its favorite. It doesn't accept yet, but it rejects everyone else other than the favorite offer that they have right then. And then each rejected proposer crosses the person they were rejected by off their list. And then we just keep repeating that forever and ever until no more offers are rejected, and then hopefully we have a matching. So that's a lot to say with words. Let's just walk through what this looks like a run of this algorithm. So first off, we need a sense of who the proposers are and who the rejectors are. So let's just say these are the proposers and these are the rejectors. Oops. And the algorithm will run a little bit different if you switch who these two are, right? But for now, let's just say, yeah, these are the proposers, these are rejectors, and let's see what happens. So first off, each proposer, the very first step, each proposer proposes to its top choice. So let's just look through that. We have the rejectors are A, B, C, and D. And let's say we're on loop 1. We're just starting. Now again, if we look back at this, the very first step is that each proposer proposes to its top choice. Very simple, right? To begin with, each proposer proposes to its top choice, which is right there. 1's top choice is A, 2's top choice is B, and so is 3 and 4's. They all have their top choice as B. So let's just reflect that. 1 proposes to A, it goes right up to A and proposes, and 2, 3, and 4 go to B to propose. Now, we're not done yet. Maybe 1 would be happy if we stopped here, but B has too many people. It needs to match 1 to 1. So to take a look at that, we need to go to the next step, which is each rejector crosses all but its favorite offer off. So A only has one choice, so there's no one to cross off. It just sticks with the choice it has for now. No accepting yet, but it just sticks with that. B has 2, 3, and 4 though. So B is going to cross off everyone other than its top choice, which if we look at here, its top choice is 2. So it's going to cross off 3 and 4. So let's go ahead and do that. 3 and 4 are gone. Let me do a different color. 3 and 4 are gone. Done. And let's see, what's the next step of the algorithm? The next step of the algorithm says each rejected proposer crosses that rejector off its list. So if we go back over here, 3 and 4 were the rejected proposers. And they just got rejected by B. So they say, okay, well, I don't need to be told twice. B doesn't want me. They're both crossing B off that list. And let's again do that in a different color. Good. So far we've done one loop of the algorithm. The proposers all proposed to their top choice. The rejectors ended up rejecting the ones that weren't their favorite. And the proposers took that into account and said, okay, well, I'm not going to bark up that tree again. Let me go on to my next top choice. So now let's go back and do the algorithm again. So now we're on loop 2, and we just start all over. So we can say, we can say loop 2. A still has 1 in hand. If you read the notes, it says on a string. A still has 1 on a string. B still has 2 on a string. And now we're going to see what 3 and 4 do, because they still need to propose to someone. So 3's top choice is C, and 4's top choice is A. So again, we just follow that. 3 goes to C, 4 goes to A. Okay, so now A has 2 choices again. We did step 1, proposers propose to their top choice. Now we're going to go on to the rejectors, who reject everyone but their favorite. Again, 2 and 3 are the only ones B and C have, so they have no one to reject. They just keep what they have for now. And A is going to reject, let's see, A's top choice is 4, which means it'll reject 1, which is, in fact, its last choice in this case. So let's go ahead and reject 1. And then 1 says, okay, A rejected me, let me record that and continue on my day. So now we'll go to loop 3. And we can do this one more time, and then I think you get the picture from there. We did walk through the whole thing in class, but we're not going to do this right now. So once again, 1's rejected, so that's the only one that needs to do something. We carry through 4, 2, and 3, but 1 is now going to go to its next top choice, which is B. Comes over there. And then the rejector says, okay, which is my favorite? B is the only one that has more than 1. And it likes 2 more than 1. So it's going to go ahead and cross 1 off of its list. Bummer for 1. 1's working its way down the list. It says, like, okay, I'm rejected by B as well. And now there's a new loop. And again, the first thing that has to happen is 1 has to go ahead and propose to C, and so on. So we're not going to go through this whole thing, but it is good to know that there is 6 loops. And at the end of the day, let me move this. At the end of the day, we end up with 4, 2, 1, and 3 gets all the way over there. So I would suggest, if you haven't done this, to just work through loops 4 and 5, just to make sure you get to loop 6 correctly. That would make sure you understand the algorithm. So we haven't done anything with the algorithm except run it. And this is good for getting a sense of the algorithm, letting our, getting a sense of how it works, what we expect from it, and helps us put it in our brain a little bit, so now we can work with it a little bit more. So what we want to say then is, great, we have an algorithm. What about it? So for example, what can we say about this algorithm? It sure did come up with a matching this time, as in let's see what that matching is. We have 4 paired with A, we have 2 paired with B, 1 paired with C, and 3 paired with D, right? So that just comes from the fact that these are where we ended up. 4 gets matched with A, 2 gets matched with B, and so on. So that's a matching. Is it good? Well, who knows, you know. D may say it's not very good because D got its last choice. D may not be happy, and D would say, who made this algorithm? This is an awful algorithm. Why would we ever do this? So if we want to say this is a good algorithm, we have to argue for that. Maybe even prove some things about what the algorithm does. So yeah, we have this algorithm. We're going to call it, we call it the proposer-rejector algorithm. It's also called the stable matching algorithm, which kind of gives a little bit of a hint of where we're about to go, but that's fine. So the stable matching algorithm, we may have questions for it. Does it halt? What if it gets stuck in an infinite loop? Many algorithms get stuck in infinite loops. I could very imagine that this one does. How do we know that it always halts? If it halts, does it always output a matching? What if someone doesn't get matched? What if at the end of it, some proposer is still left just kind of in the wind, not having anyone that they're matched with? If there is a matching, is it a good matching? How do we define good? So these are all questions we might have about an algorithm, and the question is, can we prove things about an algorithm? The very first day of class, we talked about this a little bit of like, you know, I asked how many people wrote some code and thought for sure they had it right this time. Like they had the code correct, only to run it and then see it break. And most people raise their hands. And then the follow-up question is like, okay, did you fix it? And you might think you did, but how do you know? Can you prove it? Can you prove things about algorithms? Can you know kind of for certain that your algorithm has some guarantees? So that's what we're going to be trying to do today. This, again, course moves pretty fast, and it's a bit of a survey course, but the point of this lecture, the stable matching algorithm, is a bit of a tour de force, right? We've gotten all these tools about propositional logic and Boolean algebra and different proof techniques. And we've shown how to prove very fundamental things about math, about how adding even numbers is an even number. But now we're actually going to step into computer science and kind of do this tour de force and show that the stable matching algorithm has provable guarantees. All right. So this again marks a little bit of a change of where we are, and I do kind of want to be a little explicit so that we don't get confused. What is our object of study that we're proving things about? It's the actual algorithm itself, right? We're proving things about the algorithm itself. And this also kind of creates a transition where we're at, where before we were being very precise with our definitions. And we're going to back off of that a little bit now. We're going to use all our proof techniques, but we're also not going to be as nitpicky about the definitions, because if we really wanted to talk about an algorithm, we'd have to define what a Turing machine is, so we have a mathematical object that we're making arguments about, and right now we're not going to do that. We're talking in terms of pseudocode here. So we're going to make sound arguments within a proof structure, but I do want to note that there is a little bit of a change here in kind of the level of abstraction that we're working at. So what an algorithm does is it has an input and it spits out an output. And I think the thing we want to note here is we want to be careful about knowing what is our input. For this algorithm, the stable matching algorithm, what is its input? And in this case, it's just the rankings. So if we look back up here, the input would be the set of rankings that 1, 2, 3, 4 has, and the rankings that A, B, C, and D has. So the input is the rankings itself, and the output is going to be a matching. Or hopefully, That's what we're hoping to prove, is that it always outputs a matching and no one's left behind without a partner. So some context for this. Stable matching is used in the real world, and it's used to match medical students with residencies, that is, teaching hospitals. Medical students after medical school go to a residency where they basically shadow doctors and at a teaching hospital. And there was a whole big problem kind of in the early 1900s where medical universities were offering earlier and earlier because they wanted cheap labor. So they had a lot of slots for residents, that is, medical students that were applying. So they had a whole bunch of slots open because that means they would get more and more cheap labor. And that meant the students had a lot of options. They had a bunch of options between which university they go to. So all these universities were in competition with each other to get students. And they would make their offers earlier and earlier. Like sometimes they would make their offers to juniors instead of seniors or even sophomores. And then it got so bad that they started making exploding offers where it's like you need to answer within the next hour or two. Otherwise your offer explodes. So it became real nasty. Like it became just a real stress for everyone involved, especially the students that were applying to these residency programs. So the stable matching algorithm gave a way to have students rank their favorite universities and hospitals, and the teaching hospitals to rank their favorite students and then get matched with them. You have to modify some things, but this is the basic idea. So this is a real-world example. It's also used in other cases like school choice, children being matched to public schools, which schools they want. But do be careful. This delves into normative areas where instead of just talking about math, we are talking about the real world. So normative meaning value judgments. Something's good or something's bad. So again, we've been talking a lot about translation, right? So we might be in this class where we might have something in the real world that we're talking about in natural language, and then we translate it to math, and then we translate it back to the real world. And I just want to note that we need to be real careful scoping our math, because even if we prove everything correctly in here and all of our proofs are ironclad, that doesn't mean we're saying something about the real world, because there's these translations in between that also need argument, and sometimes, often, need normative argument. And normative things about like what's fair, equitable, just, something good or bad, math can't talk about those things. That's just something outside of formal language. That doesn't mean it's not important to talk about those things. It just means we can't say that we proved a thing is good for the real world, because all we proved was something in math land, and now we need to make more normative arguments outside of that. So I just want to note that there's a paper called The Normative Gap, and that is by Zoe Hitzig. Real great paper. A little bit academic, but it's still worth a read. And I believe there's an umlaut there. But anyways, the gap they're talking about is these gaps. So, great paper. Highly suggest kind of taking a look at that paper. The main thing I want to say is that I just want to scope what we're doing. That we're going to be talking a lot about math, and there's all this, sometimes this is called jobs and candidates. So we're making a job candidate matcher. This is contentious, whether you create automated decision makers that decide jobs. Many of you may be screened through AI as you go in, looking for jobs on LinkedIn, and that doesn't always feel great. And all these decision-making algorithms in the real world are contentious things, which is why it's good to note that even though we're going to do some neat proofs about the math part of it, we can't just automatically say these are good things in the world. basically it's beyond the scope of this class. If you're interested, I believe 195 is the ethics course in CS. Lisa Yan, Professor Lisa Yan and I will be teaching a freshman-sophomore seminar next semester. So if you're a freshman or sophomore, feel free to check that out when that gets posted. On Technology, Society, and Power, I believe is the name of the freshman-sophomore seminar we'll be doing. Okay, so that aside, let's go ahead and prove some stuff about the stable matching algorithm itself. Before we do just that, no, we're going to prove this first. We're going to prove the simplest thing first. We're going to prove that it halts. Before we even define what a good matching is, we're just going to prove that it halts at least. All right, so let's go ahead and do that. Theorem, the stable matching algorithm halts. Yeah, so the stable matching algorithm always halts. And, you know, really this is saying for all inputs of n proposers and n rejectors. Right? So that's kind of hidden there, but we're going to go ahead and prove that. And we want exactly n proposers and n rejectors because we're matching those two groups of people. So there should be the same number of them. In our restricted example here, right? This is the type of inputs we're playing with. So the thing to note here is what we're trying to prove is something about the algorithm. So we need to keep referring back to what this algorithm is doing. And one thing to note is each time we're about to loop, and really we're just walking through the notes here, but each time we're about to loop, the reason we looped is because someone was rejected, right? While offers were rejected, we're going to do another loop. So we know that we can just write that out. Each loop happens because at least one rejection, right? At least one rejection happened, so that's what causes it a loop. And what does that imply? That means some proposer was rejected, right? One rejection happened, that means some proposer was rejected, and each time a proposer gets rejected, we know in the algorithm that the rejector crosses one of its proposers off the list. So that implies, let's just write this down here. Oops. A proposer crosses someone off the list. And this kind of almost completes the proof. And, you know, really this is each loop. That's kind of the whole point of this, each loop. So this completes the proof. And it's not clear immediately why, but then we need to remember that what we have here is proposers. What is their list? Each proposer, there's n of them, right? There's 1, 2, all the way down to n. N proposers have a bunch of people on their list. In fact, they have all n people on their list of the rejectors. They have all n rejectors on their list. They're just saying which one's their favorite. So maybe it likes, yeah. So oops. It has a ranking of all n people, and so does 2. 2 might have a different ranking, but it's certainly going to be all n of the rejectors, that it says, I like this rejector better than this one, better than that one, and so on. And that's true for all of them, right? These are all n people. So what happens then is we have n proposers, each having a length of n list. And what we know is that some proposer was rejected. So one of them was rejected. We don't know who. And that one proposer crosses someone off their list each loop. So each loop, one person gets crossed off. Maybe that's loop 1. and then loop 2, another person gets crossed off. It's possible that like a whole bunch of crossing off happens in one loop, but we know at least one. So now we have a limited resource, right? We know that people are going to get crossed off each time, but there's only total n squared list items. So we can't have, or the real point of this whole thing is that there is at most n squared loops. Because at some point we run out of list items to cross off. We know that each loop someone gets crossed off, and there's only n squared things to crossed off. So at some point we'll run out of people to cross off, so we can only have that many loops. That's the whole argument. This algorithm halts because the real fear is that this loop right here is the one that is an infinite loop. Right? There's this thing of each proposer. This is going to be its own little for loop. But it's a finite for loop. There's no condition. It just says each proposer. So it's for each, right? Each proposer just makes a proposition. Each rejector rejects the thing. And each rejected proposer crosses that off the list. So each one of these is its own little for loop. But they're finite little for loops where it just goes to each rejector and does a thing. Each proposer does a thing and so on. The real thing is how do we know that this will always finish? And the point is exactly this. That because this condition happens, that means an offer was rejected, which means a proposer crosses someone off the list, and that can only happen as many list items as there are to cross off. So this is the proof. And again, this marks a transition from how we've been proving things up to this point, right? We've been proving things real by the book, right? Like we've been going down to the definition of an even number is there exists a k such that it's 2 times k and so on. This is a bit more hand-wavy. And this is because we're talking a bit more hand-wavy, right? Like we are dealing with pseudocode and we're arguing about the code itself. So this isn't to say one is better than the other. It's just saying computer scientists talk at a different level of abstraction, and we prove things at a different level of abstraction. There's a way we could prove this rigorously with induction, but this is also an algorithmic proof, right? We're talking about loops and we're talking about what happens each loop, and we're kind of making note of a limited resource that we keep chipping away at each loop. So these sorts of proofs will have a little bit of a different flavor going forward in the class. And this is sort of that flavor where we can make these sorts of arguments about the algorithm and be convinced by them. Okay. So before we move on now, or moving on, let's talk about what a good matching is real quick. And then we'll get around to proving things about the good matching. So let's take a quick look and just think about this. So we're not even going to set up proposers, rejectors. We're just going to have 2 groups of people that prefer each other more or less. And again, if it helps you to think of an example, you could think of these as medical students in hospitals, or you could think of like silly things, competition shows. You know, maybe you have a cooking competition and you have people that bake sweet goods and you have people that make savory appetizers, and you need to match them. You need a team that has one baker and one savory person, and they rank each other and then they get matched for the competition that way. Or maybe you're doing a dungeon crawl in a game. So you have a warrior and a healer. Or maybe you're in a game show and you need a trivia person and someone that is a problem solver. So maybe you have trivia people over here. Maybe you have trivia people over here and problem solvers over here, and they need to match with each other. Put whatever in your brain is most helpful to you. But right now, I'm going to give you 2 different possible matchings. One is that one is matched with A. One is matched with B, and 2 is matched with A. Or 1 is matched with A, and 2 is matched with B. And the question is, which of these is better, right? And there isn't an obvious answer because, no matter what, someone's going to be unhappy. In this case, 1 is unhappy because they're with B and that was their last choice. But on this side, 2 is unhappy because they're with B and that was their last choice. So someone's always going to be unhappy one way or another amongst these two matchings. But the question is one better or not? Or at least what things seem to make it better? So just pause for a moment and think about that. See if you could see a difference between these two scenarios. So I'm assuming you paused, and one thing I'm going to say, or what we're going to look at here, is there's something a little bit worse about this one. There's some sort of instability here. And the idea here is A prefers to be with 1, and 1 prefers to be with A, right? So A, its top choice is 1. So it would prefer to go with A. And 1, its top choice is A, so it would prefer to go with A. So they both have incentive to just switch their partners, and 2 and B are just kind of left partnerless, which is a big problem. Whereas here, even though not everyone's happy, 2 would rather go with A, but A would say, no, I actually prefer 1. A is with its top choice. So even though 2 would want to move, A wouldn't. So 2 would try to leave and have nowhere to go. And the same thing with B. If B tried to leave and go to 1, its top choice, it could try, but 1 says, actually, no, I'm happy where I'm at. A is my top choice. So this is stable in some sense. Like, even though 2 and B aren't particularly happy with each other, they have nowhere else to go. So this is kind of a sense of stability, whereas here, this is a real unstable pairing. Because at any point, A and 1 could decide, hey, I'm not feeling the person I'm paired with, and they could just break apart, and then that throws all the matching off. Especially if there was more people matched over here. If they change, now 2 and B are partnerless, and what if they don't want to go together? Maybe they start going elsewhere, and that throws everything off, right? Because the instability of this can kind of break the matching. So let's go ahead and give a definition to this. A definition to this notion of instability, right? That this sort of matching is unstable. So matching is unstable means that there exists P and R. Let me make that R clear. There exists P and R that are a rogue pair. And now we need a new definition. Are a rogue pair. P and R are a rogue pair if this sort of thing happens, that they prefer each other to their current partners, that they both prefer each other. That's the key part. So a new definition. Let's just make our little definition symbol here. So that's a definition, and here's another definition. So P and R, a rogue pair, means that P prefers, in its ranking, R to its current partner, and vice versa. Yeah. So that's just this case, right? And again, a matching is a matching of all the proposers and rejectors, or just the two groups. And a matching is going to be unstable if there's two people that were matched together but aren't a stable matching. They might end up just finding different preferences. So that is, really what happens is, let's just actually write out a little example here. Or not a full example, we have the example there. But really, we're going to have, P1 with, we're going to have a bunch of matchings, right? We're going to have a bunch of P's with R's. But the point is, we might have P paired with R star, and a bunch of matchings there. Let's say like 1 is paired with A, and over here there's like 5 is paired with D, and so on. But there's going to be some P and R star, and an P star, and an R. And again, maybe there's more matchings here where like 7 is paired with, I don't know, B. But P and R are going to be a rogue pair if both P and R prefer each other than their current partner. So if P likes R more than it likes R star, and if R likes P more than it likes P star, that's an unstable pairing, because even though they were matched together, they would end up, or could end up, going rogue and just matching with each other, leaving R star and P star in the wind. And P star and R star could then match, but they may not want to. Maybe P star actually has someone, maybe prefers B, and B prefers P star. So that creates a new rogue pair. Once this breaks off, these may end up matching, even though, and then it just, kind of percolates through the whole thing. It becomes a whole problem. So this is the definition of what stability is, or really what instability is. So all something stable is saying that there doesn't exist such a PR, right? That there's no rogue pair. That's what stable matching is that there's no rogue pairs. So when we come back up here to ask, well, first off, we know that the algorithm halts. We haven't proved that it produces a matching yet. And we don't know if it produces a good matching, but what we're going to do for this lecture is we're going to say what good means is a stable matching. That's what that's going to mean for us. And again, this is a normative choice of what good means, because there are other definitions. Maybe you could maximize the number of people that get their top choice, or minimize the number of people that get their least choice. Or maybe you could try to do some averaging thing so everyone kind of gets mostly happy in an average sort of way. There's a bunch of different metrics you could do for what a good matching means. The one we're using is stable, but that's a choice. So again, I just want to delineate which part is math and which part is not. And choosing stable to be our definition of good, and especially to put that definition of good into the real world, is fundamentally a choice. Okay, but what we're saying here is this is what we're dealing with this class. We just proved halting. Next, we're going to prove matching, and then eventually that matching is stable. All about this algorithm. Because just because the algorithm halts doesn't mean that everyone was matched up. And even if everyone's matched up, it doesn't mean that it's a stable matching. So quite surprisingly, this simple algorithm, it is. Because it's quite a simple algorithm, and most of the power of the stable matching algorithm, or its historical importance here, is that we can prove things about it. All right, so let's go ahead and start proving some things. So this is the improvement lemma. I'm not going to spend the time writing it out. This is just what it is. Let's read through it together. So the improvement lemma says, if the proposer P makes an offer to rejector R on the elf loop, then every loop after that, R just does better and better. That is, R has an offer in hand that it likes at least as much as P. So let's just take a look at this. Or actually, let's go back to the beginning and take a look at the algorithm we ran through. And again, at the beginning, the proposer started off strong. right? The proposers got their top choice. It's just that they ended up being rejected and then kind of ended up getting worse and worse, right? And that's how the algorithm works, right? The proposers always start off with their top choice, but then they might end up getting rejected. So there's this kind of sense that as the algorithm goes on, the proposers start with their top choice, and then they just have to work their way down the list. So the proposers' options get worse and worse as the algorithm continues, while the rejectors get better and better. So this is really kind of the fundamental concept of the rest of all the proofs for the stable matching algorithm, is the proposers get worse and worse, while the rejectors get better and better. And why is that? Well, for example, let's say A. A ended up getting its worst choice to begin with. Not because it chose anything, but that's the only person that showed up. And then as time goes on, the other people that come, they're only going to always choose their best option. So their options can only get better and better. In this case, this stays with 4, but that's the fundamental premise. Just by the design of the algorithm, proposers are going to get worse as time goes, while rejectors get better. And that's really all the improvement lemma is telling us. That for the rejector's point of view, the rejector is only going to get someone that it likes at least as much in later loops. So this is formally saying that the rejectors get better and better. That if on any specific loop, let's say the eth loop, it has P in hand, then going forward, it only has someone it likes at least as much as P. So let's go ahead and prove this. So we're just going to go through quickly on this because we walked through the intuition already, and it's really not much more than that intuition, but we want to, use our tools. We can actually induct on this. So we're going to induct on loop K for every K that's greater than L, right? We start on loop L, and we're just going to induct on everything after L, which is what we're trying to prove, right, on subsequent loops. So the base case is just set K equal to L, the loop that we start at. And what do we know? We know that P makes an offer to R on that loop. And we know by the algorithm's design that R is always going to choose its best offer, that loop. So it's either going to choose P or someone better, right? We know that it's going to choose someone that made an offer there, the best one. So it's either going to be P that we know made an offer or someone better. And really, that's all that we need for the base case, right? That just says that R ends up with someone that it likes at least as much as P, either P or someone better. Great. So now the inductive hypothesis is simply, we just write it out. And in this case, again, we're not gonna make a huge deal of this because this is just walking through the intuition that we already said. So we're just gonna say, suppose it's true for K greater than or equal to L. What's true? That R has someone in hand that they like at least as much as P. So then the inductive step, and again, we're not going to write this out in real time. I'll just walk you through it. So, we assumed it's true for K greater than or equal to L, some K, and now we're going to consider K plus 1. So the K plus 1th loop, by inductive hypothesis, we know the loop right before it, on the kth loop, right before K plus 1, R had some offer in hand that was, call it P prime, that was at least as good as P. That's what the inductive hypothesis is assuming. Suppose it's true, meaning it has someone in hand that it likes at least as much as P. Call it P prime. So now, it has P prime in hand that it likes at least as much as P, and on the K plus 1th loop, R chooses the best offer that it gets that loop, right? So it already has P prime in hand, and it's going to choose whoever they like the most that loop, which is either going to be P prime, which is on a string in their hand, or someone better than P prime. And P prime, if they choose P prime, we know by definition P prime is at least as good as P. It could possibly be P. That's what that equal is. but we know that P prime is going to be at least as good as P, or someone even better than P prime. And if they're better than P prime, they're also going to be better than P, just by the transitivity of their ranking. And this really just concludes the proof, right? That concludes the inductive step, which concludes the whole thing, right? So this is just saying that, there's this little trick of like, well, usually we're inducting infinitely. What happens after the algorithm halts? You could define the algorithm to just kind of run forever that keeps outputting the same matching once it halts. Once it outputs a matching and says, I'm good, you could just say it just keeps outputting that matching. If you really wanted to be like super nitpicky about induction being forever. But really, this is the whole algorithm, right? Or the whole proof. Great. So this is called the improvement lemma. And that's the thing, a lemma. What is a lemma? Why did we prove this in the first place? Well, it's going to be helpful to us. That's what a lemma is. It's basically a theorem, like it's a true thing that you prove, but it's usually like a helper theorem. You could think of it like a helper function when you're writing code. It's something you prove that a theorem needs in its proof. So we're going to be using this improvement lemma a number of times going forward. This little kind of almost obvious claim that the rejector just keeps getting better and better is going to power most of our proofs going forward. All right, so let's go ahead and see what we need to prove from the top. So we proved halting, and now we want to prove matching and stable matching, that what's output is a matching, and in fact that it's a stable matching. And we're going to be using the improvement lemma, I believe, for both of those. Let's find out. So let's go on down here, open up a new page, and we could call this a theorem. We could call it a lemma. I'm going to call it a lemma because the real theorem that we want is that we get a stable matching. So right now we're going to say the lemma is that the stable matching algorithm always yields a matching. And again, it's not always clear how to prove a thing. Sometimes you need to try a bunch of things. You need to try a bunch of the techniques. But sometimes you can do process of elimination. So I'm not seeing an obvious P implies Q here. So if we're not seeing a P implies Q, that kind of rules out a direct proof and a contrapositive proof, because those are both about implication. They're both trying to prove something about P implies Q. We could try cases. I'm not sure what the cases would be. One thing that is always kind of like a guiding principle when I'm trying to decide which proof to use is what gives me something that I can get my hands on. What gives me a definition that I can immediately get my hands on. And in this case, I think we're going to go contradiction. Why? Because if we contradict this, it gives me something to get my hands on. And then I can use what I get my hands on to try to find a contradiction where something breaks. What does it give my hands on? In this case, it says that there exists a proposer that is unmatched. P, that is, there exists proposer P left unmatched. They didn't get matched to a rejector. And this is helpful to me, and this is why we might want to choose contradiction, is because now I have something to work with. Once I have this proposer, I can see just follow the logical conclusions of what it means to have an unmatched proposer and see if we can pull a contradiction out of that. All right. So let's say we have this proposer that it's left unmatched, specifically when the algorithm finishes. And what can we do from that? So if there's a proposer that's left unmatched when the algorithm finishes, that means that P made an offer to all the rejectors. Made offer to all rejectors and got rejected. P is having a hard time. And why do we know this? Why do we know that P must have made an offer to all rejectors? Well, this is why we're proving things about an algorithm, right? We just need to keep looking back to this algorithm and say, okay, what can we tell about this algorithm? And what's happening is this loop continues while there's still offers being rejected. So if P is unmatched, we know that P is proposing to its top choice every time, right? It's proposing to its top choice every time. And if it's not getting it, that must mean it's rejected. So it's going to keep going and proposing to its top choice. And the only time we exit this loop is once we're done rejecting. So that means if there was a rejector that it didn't propose to, then at one point it should, because that's still in its list. At some point it's going to propose to its top choice. And if we get outside of that loop, that means there's no more offers rejected. That means P worked through its entire list and didn't get anyone. So again, back up here to the top example. Let's say it's 1, right? Let's say 1 is just working through its list. It proposed to A, and then A rejects it. So then it proposes to B, B rejects it. And then, it keeps getting rejected. At some point, it's going to propose to C. And if it doesn't end up getting matched with C, then C is going to reject it. And it's going to work its way down the whole list. And the only time the algorithm stops is once rejection stops. And that can only happen after, let's say 1, in this case P, works through its entire list. So P made an offer to all rejectors and rejected by all of them. Real bad day for P. But that tells us something, right? That tells us something important. Because this is where lemmas are useful. By the improvement lemma, we know each rejector has a better offer in hand. Really, that it's matched with in hand than P. Why do we know that? Well, because P proposed to all of them, right? P proposed to all of them, and each rejector can only do better in subsequent loops. So if P proposed to all of them and the rejectors only get better, that means they're going to be getting better offers in hand, right? Each rejector is going to get a better offer in hand than P, and that only continues. There's going to be some P prime, just like we were talking about up here. There's going to be some P prime that it likes more than P. So because rejectors keep getting better, each rejector ends up having something in hand better than P. And the contradiction means, right, or where the contradiction is, is implications. Each rejector, not just each rejector, each of the n rejectors, has proposer in hand. But that can't really make sense, because then there'd be n plus 1 proposers, right? Because each rejector has one proposer in hand, and then there's still P left all by its lonesome. So there's n proposers that are matched with rejectors, and then there's also this proposer on hand. That's a contradiction. This is where we can say, nope, that can't happen. We found our contradiction here. Great. So this is the whole proof of that the stable matching algorithm always yields a matching. There's no way it can't yield a matching, because there'd be a contradiction if that were the case. Great. And someone asked during class, how do we know that a rejector only gets matched with one proposer? How do we know that they don't get matched with two proposers or something? Again, we need to look at the algorithm. The rejector always rejects all but its favorite offer. So the rejector, it's not like the rejector gets matched out of the blue. The matching happens, the matching happens by the algorithm, and the algorithm says the rejector only ever keeps one proposer in hand at any time, and it rejects all the others. Right, so that is now we can check another thing off the list here. Now we know that the algorithm halts always. We know that the algorithm has a matching always. And already we should just pause for a second and kind of realize what we've done. This is quite powerful, right? Like if you hadn't done proofs before, we were proving things is quite powerful and important and interesting itself. But especially if you've never proved something about an algorithm, we just have made provable guarantees about an algorithm. Not just, the algorithm seems to work, I think it works. Well, when I think through it, it should work. We've actually shown that the algorithm always halts, no matter what input you give it, and that it will always output a matching. There's no malformed output where someone's left unmatched. And now the most important part, we want to show that that matching is stable. And again, we want to remember what stable means. It means that there are no rogue pairs, right? A matching stable if there's no rogue pairs, where a rogue pair is this sort of case where you have two people that are paired with someone else that actually would prefer to go with each other. That creates some sort of instability because they could just go with each other and then the whole matching falls apart. So now we have to just continue on our proofs and finally have our theorem. We have all these lemmas. Now we're going to have a theorem. And that is that the stable matching algorithm the matching it outputs is always stable. Kind of surprising offhand. It's a very simple algorithm. Very simple algorithm. And we can prove, we're about to prove, that matching is always going to be stable. So before we do that, or it's this question of how do we even start proving that, right? Like how do we even get our hands on anything? And if you're having trouble, we can go back and lean back on our formal language. Math is at this kind of weird intermediary place when we write proofs where we're not always writing all the way down to axioms. Most practicing mathematicians, computer scientists, what have you, don't write their proofs all the way down to axioms. They live at this kind of intermediary level where they intermix natural language with formality. But formality is a tool, right? If we're having trouble with this, we can lean back on our formality to give us more structure to get our hands on. So let's go ahead and do that. What does it mean for an algorithm, for a matching to be stable? Right? It means, or what does it mean for it to be stable? It means that for all couples, we'll say for all couples, right, in the matching, P and R, if there exists an R star that P prefers, then what must be true? Think about this for a second. For every couple, if there's an R star that P prefers, what must be true if the matching's stable? We know that R star prefers its matching to P. That's the implication. Here's P implies Q, right? And why is this? Because this is just saying that it's not a rogue couple, right? That if P prefers R star, P and R star don't form a rogue couple. If R star preferred P right back, that would be instability because P and R star would then form a rogue couple and R would flock to P and P would flock to R. So if there is someone that that P prefers, some R star, then R star better not prefer it back. That would be instability. So what it means for a matching to be stable is that that's true for every couple. Every couple in the matching has this stability kind of condition happen. So hopefully this gives us a little bit more sense of how to start this proof at least. And this again is why it's helpful to okay, let's take this natural language and break it apart into formal language. Sometimes that formal language can give us a handle to start doing stuff with it. So let's start doing stuff with it. This is a P implies Q thing, which means probably we want to use direct proof or contrapositive, right? That's what they're good for. Direct and contrapositive deal with implication. So let's go ahead and try direct, right? So let's do a direct proof. And remember, direct means we assume P and see if we can show Q follows, right? So, this is supposed to be for all couples. So let's consider an arbitrary couple. Consider couple PR in the final matching. So if we have the couple P and R in the final matching, then we can say there exists R star, or this is our setup, right? We start with PR, and now we're assuming the antecedent. Now we're assuming P, and we want to show Q. So P implies Q. So let's assume the antecedent. There exists R that prefers. That P prefers. That P prefers to R. And let's just write it out, right? This is how we do proofs, or how it can be helpful to do proofs. We want to show the consequent. That is, we want to show that R star prefers, prefers the pairing it's in. It should prefer the pairing that it's already in as opposed to moving to P. So let's go ahead and prove that. So what do we know? Since R star is higher than R in P's list, right? We know this. We know R star is higher than R in P's list because P prefers R. P prefers R star to R. So we know P prefers R star, so R star must be higher. And by the definition of the algorithm, P proposes to its top choice always. It crosses things off that list, but it's always going down the list. So we know, since R star is higher in R than P's list, P must have made an offer to R star already. Before it got to R, must have made offer to R star already. It wouldn't get to R without going through R star first. That's how the algorithm works. P works down its list, right? But that must mean R star must like its pairing more than P. Why? By the improvement lemma. Remember, the rejectors are always getting better and better, right? They never get worse. That is, R star at some point must have rejected P in favor of its current pairing. And it's always going to get better and better pairings than previous loops. And P must have been a previous loop because it must have already proposed to R star already. So this is the argument, right? This is the direct proof. And look how short it is now that we know the improvement lemma and that it always outputs a matching. Once we have these lemmas, they really do a lot of heavy lifting for us. So now we can say, yes, the stable matching algorithm does indeed output a stable matching. That's why we now call it the stable matching algorithm. Great. So that really does it for the stable matching algorithm. As in, like, we've shown, you know, let's celebrate now. We've shown all three of these. Celebration, right? We've gotten that the stable matching algorithm always halts, that it always produces a matching, that it always even produces a stable matching. So what more is there to say? Well, you know, there's kind of always more to say. Again, our object of study right now is the algorithm itself. So what more can we learn about the algorithm? And we didn't get to this in the live class, so now this is the rest of the part. And now we're going to be talking about, we want to go back here. Now we're going to be talking about some more nuance. Yeah, we won't talk about that. In the notes, there's this nice little roommates problem. Work through that. That's nice. It just shows that stability isn't guaranteed. This is actually quite surprising because, like, you could imagine, or you might think, that there are some rankings that people make where stability is impossible. That stability just never happens because the rankings are just that way. Where no matter how you match them up, there are people that would actually prefer each other and then the whole matching breaks. And this is actually true in what's called the roommates problem. So if you didn't have these two lists, if you didn't have two separate types of lists of, you know, medical students and residencies, or bakers and savory specialists, and trivia people versus problem solvers for a game show. If you didn't have these two separate lists where they're matching each other, if you instead just had one list, right, just cross that out. If you had one list and they were all ranking each other, this is the roommate problem, where they all want to decide which roommates they want, and they're all choosing amongst each other. That has things that are fundamentally unstable. There are some rankings where no one will ever be happy, and it just constantly churns, where, like, rogue pairs break off and create a new matching, but then those have rogue pairs that create off and make a new matching, and so on and so forth. So look through the notes. The roommate problem is a cute little example, and it's neat to see. And it makes this all the more surprising that that there is, in fact, always a stable matching, and that the stable matching algorithm finds it. How do we know there's always a stable matching? Well, in this case, we didn't prove it that it just exists. We proved how to construct it. So because the stable matching algorithm always produces a stable matching, there will always be a stable matching. This proof proves both. Quite powerful, quite surprising. So the rest of this, we are going to talk about optimality. Okay, so I'm just going to pop this up for you. This is another example. We're not going to look too closely at it. But again, we have rankings. 1, 2, 3, 4 rank A, B, C, D, and vice versa. A, B, C, D rank 1, 2, 3, 4. And I'll tell you, there's two stable pairings here. There could be more than one stable pairing, right? Like there's nothing that says there can't be. And in fact, here's the only two that there are. These are two pairings, and I'll just let you know right now, they're stable. There's no... there's no rogue pairs of like 2 wants to go with A and vice versa. These are the two stable matchings possible from these rankings. Okay. And the question is, well, they're both stable. Is one better? If there's multiple stable pairings, which one will the algorithm output? And is one better than the other? Again, so there's more nuance to this algorithm, right? Not only does it output a stable matching, but what if there's many? Which one does it output, and how do we know it puts a good one out there? So for example, like, how do we know which one's better here? Take a look at it for a moment. Well, like, if we look over here, this is better for 2. Right? Like, if 2's match with D, it likes D more than it likes C. So on this side, 2's happier. Yet, on this side, this is better for C, right? C would rather be with 2, than it would be on this side with 3. So one side's better for 2, one side's better for C, so it's not like there's a clear-cut winner. So which one do we call better? And now we're going to give another definition. So this is the definition. We're defining something called the optimal rejector for proposer P. That is P's optimal rejector. The person P would want the most in a matching that works is this. For proposer P, the optimal R is the highest ranked rejector on P's list that P could be paired with in a stable matching. And this part, I can't stress enough, is so important. It can get real easy to be confused about this part, or to forget this part. And it's not saying P's optimal choice, right? Because like if we're talking about 2, right? 2's optimal choice is A. But that's not one of the stable pairings. In neither of these, of the 2 stable matchings, 2 never gets paired with A. So it's not that 2 gets its top choice. It's saying which choice is best for 2 of the stable matchings. So in this case, its optimal stable matching, since there's just 2, is D, right? Because D is what it prefers over the 2 possible stable matchings it could have, right? So don't forget that we're restricting the set of things that P's looking at to be the possible stable matchings. So that's what it means to have an optimal rejector for proposer P. Optimal meaning the best possible outcome of the actual feasible outcomes. And we're only saying things are feasible if they're stable matchings. Right? So, and let's take a look at this to develop a little bit more intuition. So we looked at 2 and we looked at C. What about 3? Well, let's look a little simpler. What about 1? Well, 1 gets paired with A both times. So, and it's also its top choice, so whatever. Like 1 can't do any better. A can't do any better. A wants to get paired with 1. So these are just, there's no difference between these 2 pairings for them. And the same with pairing 1 and 2 here, right? B is not 4's top choice, but they're the same across them. So it's not like 4 could do better across the set of stable matchings that there are for this problem. And the same with P. No matter, 4 happens to be its top choice, but no matter what, it's going to get its, or no matter what, they're going to get paired in a stable matching. So really the only thing left to look at is 3. And in this case, well, let's see, 3 does seem to prefer C to D. So on this side, this is actually better for 3. And what about D over here? Well, this side is actually better for D. So this is a little interesting what we have right here. It seems for let's just call these the proposers and these the rejectors. It seems that if we're talking about the rejector or the proposers being the numbers and the rejectors being the letters, this pairing is universally better for the proposers, whereas this pairing is universally better for the rejectors. There seems to be this kind of split, that these pairings are actually split across which are better for proposers versus rejectors. Kind of surprising, but let's look at that actually. Let's look at some intuition. So in math, draw pictures. Any chance you could get. It doesn't have to be rigorous. When you get down to the proof, that's where you want to be rigorous. But everything in between, hand wave, just draw diagrams, be loose about it, because it helps you develop intuitions. I draw pictures like this all the time when I'm doing research. So let's make a line and say on one side is proposer's top choices. And on the other side are the rejector's top choices. So the key thing here is, where do we start? Where does the algorithm start? The stable matching algorithm. Just take a moment to look at this. On this really loose, informal picture, where does the algorithm start? Well, let's look. At the beginning of the algorithm, very first thing, each proposer chooses its top choices. That's where we start, right? So at the very beginning of the algorithm, the proposers get all their top choices. You know, that's not the end of the algorithm, and that's not where the matching goes, but it starts with the proposer's top choices. And again, like we've been saying, the proposers only get worse from then on. Well, the rejectors get better. Like, we're moving from this side to where the rejector's top choices are, right? So again, this is an informal diagram. What is this line? I don't know. I didn't give it an actual metric or make this formal. But there's this sense that proposers start here and continue on there, and rejectors get better and better the further the algorithm continues. So we're going to say this is the algorithm. It goes in that direction, and we start here, right? We start on this side. And then at some point in there, there's going to be a whole pocket of stable matchings. You know, maybe there's only one, but we just saw a case where there's two. You know, here's two stable matchings for an instance. So we might hit this whole pocket. In fact, you'll show that there could be many on the homework. You hit this whole pocket of stable matchings, and we're going to stop once we hit the first one, right? That's how the algorithm works. Once we find a matching, we're going to stop. And we know that it's going to be a stable matching. That's what we proved. We proved that it's going to output its first matching, and that will be a stable matching. So since we're kind of moving this way, the first place we hit, like the first pocket that we hit, or the first place we touch that pocket of stable matchings, a special thing's going to happen, is it's going to be what's best for the proposer's top choices. We'll call this proposer optimal. And let's give a definition real quick so we actually know what proposer optimal means. Okay, so here's this definition, right? A matching is proposer optimal. That's our definition, is proposer optimal if all proposers get prepared with their optimal rejector. What does that mean? Well, this, right? Like this definition up here. A whole matching is proposer optimal if every single proposer gets their optimal rejector. That is, they get the best rejector they could within that pocket of stable matchings, right? In a stable matching. So that's a pretty powerful thing. It's pretty, like we were looking at up here, that this pairing is actually good for every single proposer. Like, it's good for 1, 2, 3, and 4. It's the optimal they could do. Whereas this side is optimal for A, B, C, and D, the rejectors. When we decided that one's proposer and that one's rejector. So it's a pretty powerful thing, and you know, well, the real surprising thing is not just this definition, but this theorem that the stable matching algorithm always produces proposer optimal matching. So just take a moment, because how surprising is that? That the algorithm not only puts out a stable matching, but it's the one that is best for the proposers. Like, as far as stable matching goes, for every single proposer, it's the best they could have hoped for amongst the stable matchings. That's quite surprising, especially for such a simple algorithm. So, analyzing an algorithm can be so powerful, especially when you have all these tools we've built up, all these tools of proofs. you can say pretty powerful things about the algorithm itself. Yeah. It turns out that the algorithm is not just proposer optimal. You know, as we start the algorithm here and go here, and this diagram you won't see in the notes because it's not formal. This is just how I think about things. So drawing these sorts of pictures isn't a formal proof, but it helps you gain intuitions for kind of how the algorithm works. It's this kind of notion that the proposers always start and get worse and worse while the rejectors get better and better, or not get better and better from this direction, but get better and better from this direction. We start and go towards the rejectors' top choices. And as that happens, we kind of hit this pocket and we hit the first thing that's, we start with the top choices and go down until we hit astable matching. And because we started from the best choices for the proposer, the first thing it hits will be proposer optimal. And bad news for the rejectors is we stopped going closer towards the rejectors. So this is actually rejector pessimal. Which is to say that the rejectors get the worst choices they possibly could have out of all the stable matchings. Like if you look at all the stable matchings, each rejector gets its worst choice, which we can see in this example, right? Like this pairing was proposer optimal. It's the best for all 1, 2, 3, and 4, but it's the worst for A, B, C, and D. Like we saw that it would have been better for C to be on this pairing and better for D to be on this pairing. So if we ran the algorithm, this is the pairing that the stable matching algorithm would produce if you set these to be the proposers and these to be the rejectors. So it's actually powerful which one you choose, right? Like if you swap these, if you swap the proposers and rejectors, it would output this pairing, which would be the best for A, B, C, and D, and worse for 1, 2, 3, and 4. In fact, the matching algorithm, or the stable matching algorithm for residencies, for medical school, actually used to have the hospitals be the proposers. So it always worked out in their favor, right? Like they always got the proposer optimal conditions. They were the proposers, so they got their best choices amongst all the stable matchings. And in the 90s somewhere, it was actually switched. So now the students were the proposers. So like it is quite surprising. You can make these small changes and it has huge differences on the algorithm. And again, that's one of those normative choices. So yeah, there's another theorem here, and we haven't proved either of these yet, but really it's the same as the one above, except it's rejector pessimal. And, you know, I'm not defining these rigorously right here, but that's what the notes are for. If you want to really kind of like look at the definitions and kind of sit in the definitions, the notes are very rigorous on these sorts of things. So there's a question of whether we want to prove both of these. Let's see. Yeah, let's go ahead and prove this one. This one you can basically do by contradiction, by saying if this theorem is true, if the stable matching algorithm always produces a proposer optimal setting, then you can use that in doing contradiction for this. And I don't think I'm going to prove that one. That's a short proof, but it's in the notes. I'll let you prove that one. Really, you know, the homework isn't going to have you reprove these things. This is just good to kind of get a sense of what optimality means, think through what an algorithm does, and all the nuances of an algorithm. And really, this is just trying to give you a little bit intuition that the notes may not give, of kind of what optimality looks like, and how you can try to think through an algorithm, and think through the notes. So let's go ahead and prove this one, and then we'll call it a day. And I'll try to get this video out to you as soon as possible. Okay, so let's just run through this proof. I'm just going to walk you through it. So again, we're proving that the stable matching algorithm always produces a proposer optimal matching. This will be the last thing we do. So the way we're going to prove it is we're going to induct on K, where K is the loop, so that let's say no proposer gets rejected by its optimal rejector on loop K. That's what we're trying to induct on. We're trying to make sure the proposers never get rejected by their optimal rejector in the stable matching algorithm. If they get to the end and never get rejected by their optimal rejector, then they'll get at least as good as their optimal rejector, and you can't get better than your optimal rejector. That's why it's optimal. So this proves that you'd end up getting your proposer optimal matching if we can prove this induction right here. So let's just start off in introduction and make sure you're clear why this would prove the theorem, right? So base case, let's just start with k equals 1. And we're going to do contradiction. Again, that gives us a handle on something. If we do contradiction, then we have a proposer in hand. We have something that says, yeah, we have a proposer in hand, and then we can argue about it. So contradiction, let's say there was a proposer that was rejected by its optimal rejector. Let's call it R. So let's say proposer was rejected by R. And let's call this proposer P right there. Yeah. So if it was rejected by its optimal R, that means there's some P star that R prefers. R prefers P star, and P star must have proposed to R because it's day 1. So if P is getting rejected, that must mean it's getting rejected for someone else. That is, there is some other proposer that's proposed on that day, and P got rejected because of it. So that means P star prefers R to all the others. We know P star also must prefer R, right? P star must prefer R to everyone else because it's the first loop. The first loop, P star, by the definition of the algorithm, the proposer just chooses its top choice. So P star chooses its top choice. P star chooses top choice R. So now we know that P star prefers R, and R star prefers P star. Right? That's why R chose P star and rejected P. That means R and P star will be a rogue couple. So if R and P, that is an optimal pair. Remember, we're saying contradiction, that P rejected by its optimal R. P and R are optimal. So if R and P ever got together, then R and P star will end up being a rogue pair. That is, R would rather go to P star, and P star would rather go to R just by this argument right here. So if R and P ever end up together, we have a rogue couple, which means it's not stable. Contradiction, because R and P have to be stable by definition of optimality. Optimality is, again, talking about optimal within the pocket of stable matchings. So just by assuming that R and P are optimal to begin with means that they must be stable. So if it ever gets rejected by its optimal rejector, then we follow this logic and find a contradiction because there must be a rogue couple. So that's the base case. We found a contradiction of it being rejected. Okay, so now let's go ahead and finish the proof. We're just going to scroll down here and do inductive hypothesis and everything that we know. Okay, so the last stretch. Again, we're just going to walk you through it. This is the last bit of it. Here's our inductive hypothesis. Just say it's true for K, some positive loop K. Again, what are we saying is true? That no proposer gets rejected by its optimal rejector on loop K. So we're assuming that no proposer gets rejected on loop K, and now the inductive step is consider K plus 1. Again, we're going to do contradiction because it gives us a handle on something. If we do contradiction, now we know there exists a proposer P that gets rejected by its optimal R. Yeah. So there exists a proposer P that gets rejected by its optimal R on loop K plus 1, which must mean that there was some proposer P star that proposed on loop K plus 1 that R preferred. R prefers P star to P because that's when P got rejected. Is P star, again, for the inductive hypothesis, no one got rejected by their optimal rejector yet on loop K. And now we're saying on loop K1 it happens. On loop K1 it happens because there's some P star that proposes on that loop. that beats out P. So now we know that R prefers P star, and we're going to argue that P star also prefers R. Why do we know that? Well, P star likes R at least as much as it's optimal. It could be its optimal, but it likes it at least as much as it's optimal because it hasn't been rejected by its optimal yet. That's the inductive hypothesis, right? I should have written by inductive hypothesis here. Let's just go ahead and do it. By inductive hypothesis. Yes, so no one got rejected by their optimal in loop K, so that means P star hasn't been rejected by its optimal, but still chose R. That only happens, again, looking at the algorithm, that only happens if it likes R at least as much as it's optimal, because the proposer is always choosing its top choice. So if P is choosing its top choice, it must like R at least as much as it's optimal, because it didn't need to cross its optimal off its list because it didn't get rejected by its optimal. That's the inductive hypothesis. So it likes R at least as much as it's optimal. So that means that P star prefers R and R prefers P star. That means P star and R is a row couple. This is just like the argument here. We're just doing it again. Have to do a little bit more argument because like here it wasn't, because it was loop 1, we know P star prefers R because it's choosing it there. A little bit more argument by inductive hypothesis, but really we're getting that P star and R are a row couple. That gives us a contradiction to P and R being optimal because it must be stable. That's the definition of optimal. So the same argument that we used here, just rewind and look at the argument we used here if you need to. But that gives us our contradiction, and that concludes our inductive steps. So that proves the whole thing. That proves that it always produces a proposer optimal matching. Go ahead and read the notes for rejector optimal matching. Again, you're not going to reprove these for the homework or anything. But these are just powerful, surprising things. And as you think about the homework, think about what it means to be a solution to something and optimal, that there's a whole range of possible stable matchings. And deciding what's optimal is choosing which of the possible stable matchings you like. So hopefully this helps you get through the notes a little bit easier and is useful to look back on as you do the homework and so on. Again, sorry for the audio just completely cutting out. Hopefully this is helpful. All right, good luck, y'all. And come to office hours, work in study groups.